about Chan-Vese model for active contour creation without aging. My presentation today, it has two main parts. First part is introduction about the technique that's already used, and in the second part, I will go through the Chan-Vese model, and I had planned to go to the detail of the numerical implementation, but I found a code in the MATLAB, and if we have time at the end of the presentation, I will show some demos of the code. Okay, let's start with introduction. Today there is two kind of contour detection, two type of the active contour detection. The oldest one, the technique that there was a lot of papers that published on that, is the snake model, and the second one is geodesic model. In the snake model, there is an object function called we call it J1 of C, which is equal to alpha integral of 0 to 1. I will introduce each part of the this objective function. And first derivative of C. C here is the curve that we're gonna draw it around the object in the image, and S is the parameter to parameterize the curve. Absolute value plus the integral of 0 to 1 of absolute value of second derivative of curve ds plus integral 0 to 1 of u0 cs dx. The problem here is we have the image, entire image, we call it omega, and we have some object inside this image, and we wanna fit a curve around this object. For example, let me draw something like this, and the image is not very clear. It's may have noisy, or it has unsharp boundaries, and with the snake model that I wrote the objective function of that, the objective here is we want to have a curve around the object that it has as less as possible discontinuity in the curve. For example, if we want to try to find the edges in the image, the result may have something like this in the image, and we don't want to have the edges that is not connected. And the first step, try to force the objective to have a connected boundaries. And in the second step, for example, consider a case that the object, it has a lot of noise here, or it's blurred, and if you wanna fit the curve, it can be the curve something like this with a lot of corners. And the second then try to push the boundary of object as smooth as possible. And the last term is try to stop the function of fitting when we are in the way that the gradient of the function is the minimum. when we have the minimum gradient, we wanna stop the fitting process and say, for example, this is the boundary of our. This is some whole idea of the technique, and the objective of function for the snake model is to find the point that it has the minimum gradient, but the objective is try to have a smooth curve as a boundary. Here, from now on, the entire image that we have, we call it omega, and the curve that we want to fit, we call it C, which is equal to root of omega.
What's the omega?
Omega is the entire image, and the C is the boundary in the image that we want to. Oh, okay. Yeah. Yes.
What's the meaning of U0?
U0 is the intensity of the image. Intensity of the image. For example, each pixel on the image, there is an intensity value between, for example, 0 to 255, and this one is the gradient of the.
What gradient?
The gradient means, for example, if consider simplest possible images. For example, we have an image with only two areas. One is absolutely white, and the other is absolutely dark or black. And the gradient here is equal to, for example, 0, because there is no changing in the intensity, and the gradient here also is 0. But here we have the biggest changing in the intensity, and it's create a big portion here, big term here, and okay, sorry, here is minus, and we wanna find the infimum of JC over the curve C, and if this term is big, the result will be the infimum of the infimum of this objective function will be our objective. The infimum is the greatest lower bound. For example, if you wanna have if you have an infinite set, not infinite set, the unbound set, and there is no minimum and there is no maximum on that. But if you want to find the infimum of something in this set, is the greatest lower bound of the function. For example, you have a lot of things that is the minimum of something, but the biggest one shows the somehow the boundary of the object. Okay, this gradient here, it's some edge detector, and in the for the edge detector function, it must have we can use the some function as edge detector on the intensity. This kind of function must have some properties. The properties of the function, the edge detector function, they must be positive, decreasing, and the function must be dependent on the gradient. From now on, we used g of, for example, gradient of the intensity. It can be a function that must be positive. It must be dependent on the gradient, and it must be decreasing. For example, if I want to have an example of this kind of the function, it can be 1 over 1 plus the
What was G?
G is a function that is dependent on the gradient. Because we need a function that's based on that, we wanna push the curve and force on the curve to move into or fit to the object. And it can be one example of this kind of function. For example, the p if is bigger equal to 1. It has all of the properties. It's positive always. It's decreasing, and another thing, the limit of g when, for example, g of z when z goes to infinity. It must be equal to 0, and it means we don't have any edge infinitely far. Yes. Okay. The curve that we're gonna fix over the object here, we call it C. This C is equal to the set of xy points where there is a phi function xy is equal to 0. This phi function can be, for example, 1g, that we want to have these properties. And the rate of changing the phi over the iterations is defined as rho of phi over t, rho t, derivation of the phi to the t is equal to the absolute value of the function plus a force, which here this force is divergence of rho phi to absolute value of the phi.
Phi is not dependent on the T.
Phi is in the image. For example, in the image, the phi of x it's declared the area that. Let's consider this case. For example, we have a function, some bowl-shaped function. Okay, this one is phi, and consider this point is equal to 0. Okay. In our problem, if you can consider a phi for each point in the 2D space, for example, x, y, and z. Z is the value of the phi, and in the 2D we have the image, and the level set phi equal to 0. It's the curve that we wanna draw in the image to separate the image. One side, for example, inside the curve, and the other is outside the curve. The value here, the curve is the point that the phi is equal to 0. The value is plus is inside, and the value is minus is outside of it.
To explain the first two terms again.
Yes, the first term, the first derivative of c means we don't want to have infinitely disconnect point in the if you disconnect point in the curve, for example, if we try to find the edge detector, edge in the image, the result can be something like this. For example, some edges, something like this. And if you have a discontinuous value, this creates a big change, and also we don't have the first derivative. And because of this, we want to have the curve that is connected. And the second term is if you have a corner, this value, if we have very sharp corners, the value here is so big and it's increased this value.
What's the derivative with respect to this derivative with respect to what? Yes.
S is the parameter that, for example, you can have a range of S. For example, S can map the value, have the value between 0 or 1, and it's mapped. It mapped the value to the R. In this case, for example, we can have for example, C of x, y. Here the curve C is the magnitude between 0 to 1. If we change the S from 0 to 1, we parameterize the curve of CS. If we change the value of the S from 0 to 1, we have the whole curve in the omega.
But you don't know where's the curve, right?
Yeah. Based on the gradient function, you want to find the points that it has a maximum gradient, and the curve is some closed curve and with no sharp corner.
Yes, but I was trying to understand the rotation at the first time. Like, if I assume I know CS, what's the interval really going for? Like, your C is.
The C is a parameter between 0 and 1. When you do the integral from 0 to 1, it means you.
You mean the S, right? S is 0 to 1.
Yes, S is 0 to 1. When you try to find the integral from 0 to 1, it means you trace all of the curve once.
But you also use C as a rotation as the area, right? As a function of S, right? You have an omega instead, right? Omega is like a.
Omega is the entire image. C is a curve. Oh, C is a parameters that. Oh, sorry, C is a curve. S is a parameters that with that you can trace all of the curve.
So which one is equal to 0 inside or outside the.
We define for the C, we use a phi function.
Okay.
Yeah, the phi function is the function that we want to define that it's equal to 0 on the boundary.
Okay.
And this boundary is the boundary of the object. Okay. here we have rho t is equal to absolute value of phi divergence of rho phi to absolute value of rho phi. Here we have three parameters. First one is t. The t is time that we start to, for example, iteration to find the, for example, we start with some initial curve. The initial curve we call it the phi of 0 x y is equal to phi 0 of x y. For example, in the start, we start with one arbitrary curve. Doesn't matter what's the shape of that. We start with that one, and we increase the time. And in each iteration, we change the xy to go to the points that we have edge, and we have a smooth boundary with less possible corners. And here the t is between 0 and infinity, and x and y belong to r square. In the original version of the snake model, the changing of the curve is depend on the absolute value of the gradients of gradient of phi and divergence of this thing. In the geometric models, here the changing, we need to stop somewhere. When you start to changing from the initial point, you need to stop somewhere. And here, if the gradient of phi is equal to 0, is the condition that this changing of the phi over t doesn't change, because this one is the equal.
Are you guys have any questions? Do you have questions?
Oh no.
Okay.
I view on my side if I
Okay. Yes, I can hear you.
yeah, actually I view this side and listen on his presentation. If I open my
I know that's echo probably.
yeah.
Okay.
Yep. Okay. Let's keep this one and go to the yeah, I think we don't need this object function anymore. And the other family of this kind of method called geometric active. Here the changing, this one is based on the mean of the curvature. Here the changing of the curve over the time is dependent on the g function that we introduced before, and we had the example of that. The g was g of, for example, g of z is equal to 1 over 1 plus some Gaussian function, multiple the value that we have here is this is the intensity C, power P, that P is bigger and equal to 1. Okay, this is some Gaussian function to decrease the amount of the nodes. For the geometric active contour, the rate of changing the phi is dependent on this function, which is dependent on the gradient of u0. Here is u0 is the intensity, multiply the absolute value of this function and the divergence, and phi over plus a regularization term nu. Here again the t is between 0 and infinity, and x, y are in half.
So what do you mean by the derivative of the phi over t?
Okay, derivative phi over t shows the changing of the curve over the time. You start with some initial curve and you want to change it based on the curve in each point of the image. For example, if this is the initial point, you have some gradient here. It may have some direction and some value. Okay. Based on this direction, for example, somewhere is here, somewhere is equal to 0. Okay. Here you want to move in the direction of this gradient, and for example, you want to push the curve here and push back here and fix this point. And when this term is equal to 0, it means you are the point that phi is equal to 0, and your curve is on the boundary of the image. Because of this, based on the technique that you wanna change the curve, there is some problems to, for example, converge to the speed of the convergence. And in the first one, it was the basic one. It was only dependent on the force that was dependent on the gradient in each point, and the value it was the absolute value of the gradient. But in this case, there is one regularization point, which is the nu is bigger than 0. It's always force the for example, if this value is small, we have a big nu here that always push the boundary to moving, and it's help if you are close to the points that we have the minimum gradient. This point push the function to move faster and have a and also it push the boundary to the object, because if you are close to the boundary, may the curve movement is very slow, but this one push the it's a force to the function, to the curve, that push the curve toward the object. And here again we have some initial curve that we start. Here the movement is dependent on the speed of movement is dependent on the g and the curvature of the c in each point, and nu only increase the speed of the movement. There is another one that is similar to this one. It's the reference 14 of the paper of the name is active contours without edges. In this model, the changing the phi function is depend on the absolute value of the gradient, and they define a positive value nu. Okay. Here, if the gradient of the u here is the intensity, u0 is the intensity of the image. If the gradient of the some Gaussian function multiple to the intensity of each point, it's it has a range between minus between m1 and m2. m1 is the minimum magnitude of this one, and m2 is the minimum value, and m2 is the maximum value. And if we reach the point that the value is the m1 is maximum and m2 is the minimum, and if we reach the point that we have a maximum value, this term is equal to this term is equal to this one, and nu minus nu is equal to 0, and the function is a stop.
The maximum value in the some area, or
here in your curve, this is the curve, and you have a gradient. You can calculate the gradient over all of the image. And when your curve is the point that this point has a maximum value of the gradient, and the push here is equal to 0. And the curve here doesn't change. For example, if you have a curve that goes here, it doesn't change. But the area that is close to that, it's depend on the value of the gradient will change. Okay. And all of these three type of function, the first one, second, and third one, are in the family of the snakes model, and in the geodesic models, the object function is different, and they work on the Romanian space. Really, I didn't go to the detail of that, and now I wanna go to the Chan-Vese model. That is the model that was proposed in the paper. The main idea of the this model, we start from the some simple idea. If we have an image that there is one object inside that, we want to have a curve that's if this curve, if this is a curve, we want to have f1 of c plus f2 of c, which is equal to integral of inside c on intensity of x, y minus the some constant value c1 which we will introduce in the continue, that this one is the average intensity inside the curve, s square dx dy plus the integral outside of C of u0 x y minus c2, which is average of intensity outside of the curve C. We want to have this one equal to 0. It means we want to have a curve that there is in the inside of that there is nothing that is different from the object, and outside of that everything is more or less symmetric. This is the main idea of Chan-Vese model. But still there is some constraint that we want to satisfy. One of the biggest, most important constraint here is we don't want to have the very, I can say for example, we want to have a sharp and a smooth contour. It means we want to have the minimum contour around each image. Therefore, in the objective function, we want to have some terms that try to minimize the distance, the length of the curve.
Excuse me?
Yes.
So do you mean that the right one is the curve, and you want to shrink the curve that the curve is match the image?
Yes. This is the initial curve, and we want to shrink it, or
Oh, okay. So based on the equation
it's
you
not
just
necessary
talked about previously,
sorry.
is how to shrink this curve is based on the equation you just talked about previously.
And no, I will introduce in the future how I
Okay.
can. And it's not the case that the curve is outside of the image. The curve can be anywhere. It's, for example, if this is the image, the curve can be, for example, something like this. Or
With the initial curve.
initial. Or maybe something like this or this.
How we can find the initial curve?
It's really random.
You just find the random curve?
Yeah, you find a random curve, and after that try to update the curve by that function that I will introduce in there. Okay, in the simplest case, we want to have this one equal to 0. It means the curve, if the first term is this integral and the second term is this one, we want to have the f1 of some c0 plus it's not exactly 0, it's close to 0, plus the f2 of c0 is equal to 0.
You need to mute this.
Okay.
And now we want to add the two terms for having the very the smallest possible length for the curve. If we call the function f of c1, c2, and big C, which is the curve, is equal to some constant, positive constant, multiple the length of C plus the nu multiple to the area inside C plus plus lambda 1, the integral of inside, let me call it inside C of u0, the intensity of xy minus c1 squared dx dy plus lambda 2, the integral of outside C of u0 x xy minus c2 squared dx dy. Okay. In this, we want to find the minimum of this function. It means we want to have the shortest length of the C with less minimum area, and the outside of the inside of the curve is more or less similar. In the paper they call it piecewise constant, and the outside is more or less similar. Okay, this is the objective function of the Chan-Vese model. Before for the proof of convergence and to prove that there is we can find a curve that can satisfy the condition that this curve is global minimum of this function. There is a relation between this method and the method that's before used for the image segmentation. They call it Mumford Shaw. They are two names of the authors of the paper. In this model, the f of ms, which is m and s from here, of u, the intensity at the curve is equal to the mu length of C plus lambda C the intensity of xy minus the plus the as I said before, this function is some it's inside this function, because we assume that the image inside and outside is piecewise constant, and because of this term is equal to 0. This term means the length of the curve. This is the intensity, and this is the value of the curve. This function u is equal to average of C inside, and is equal to average of this u function, it has a value which is equal to average of 0, where this point is inside C, and this is the value, average value where the point is outside C. Okay, and this term is equal to these two terms that we have here separated, and this term, based on our assumption that the function is piecewise constant, is equal to 0, and the whole thing here is the subset of this function. And there is a proof for this function that it can converge, and because of this, in some special case that in the paper they assume that nu is equal to 0 and lambda 1 and lambda 2 is equal to 1. It's a subset of this one, and it will have the minimum, or it has a minimum value. Okay. For now, I want to go a little about to go through the technique that you can implement this one for coding. First, I read the paper, and after that, I try to find this code. That unfortunately I found that, and hopefully I can show some demos of this paper. Okay. Let's go and see what's the if we try to formulate this problem with level set formulation. We have a C, which is the curve that is inside the image, and C is equal to of omega, which is equal to the x, y on the image, where the function phi x, y is equal to 0. And let's call it a small omega, and the small omega here is inside image, inside curve C, and the omega, this sign is equal to outside of C. Here, for example, x, y again in the omega, and phi of x, y is bigger than 0, and here the phi of x, y is equal to less than 0. Here is inside, and the other one is outside. We can have a function, a step function of Chan-Vese function h of c 1 or 0 if the c is bigger than 0 and c is less than 0, and delta 0 of c, which is equal to dhc dz. If I wanna rewrite everything here based on this function, the length of c is some parameters. Here is some parameters. This is the definition of the h. Now I want to rewrite everything based on the hc and delta 0 of c. Okay. The length of C.
I guess you'll have a stat function effectively writing more like now you're writing more like a stat function, right? H is not like stat function, right? It's more like
Heaviside function.
yeah.
In the 1D is.
But if you start stat function here, you cannot take derivative.
Oh, you mean this one?
Yeah. Oh yeah. Okay. Okay. You put a delta function. Okay. Yeah, that's fine.
We didn't use this function. We
Yeah.
have an estimation of that. This function is it's 1 then and 0 here, and the derivation of this is some, for example, this one and 0. Here we have the curve that is something like this, and the dh to dz something like this to do the numerical analysis to find the curve. But first assume it's this one, and after that we can replace everything with this curve function. Okay. If I wanna write this term based on this function, the length of C is here. It's the point that phi is equal to 0. I use phi is equal to 0 is equal to the integral over omega of the delta h of phi xy dx dy this one is equal to integral of delta 0 of phi xy absolute value of xy dx dy. This is for the distance, and for the area of phi inside the C, which is bigger than 0, it's equal to integral of h of phi xy dx dy. And for this term, finding the somehow similarity of point inside the curve, we have the integral of phi bigger than 0. It means this point is inside the curve, which is equal to intensity of xy minus c1 square dx dy, that I can rewrite it as omega of 0 of xy minus c1 square multiple h of phi xy dx dy. And for the area that is outside, we have the same thing, minus C2 and 1 minus h of xy. Okay, now we have everything based on this function, and if I call here big A, B, C, and D, the function of f, c1, c2, xc, which here we use the function phi to introduce the c, and both of them are numbers, because here we replace everything instead of the c with the phi of xy. Let me change it to the phi. Is equal to lambda A plus nu B plus lambda 1 C plus lambda 2 D. And here we can keep the phi as a fixed constant and try to minimize this function and respect to the C1 and C2. And here you can see if I assume the phi is the fixed, and I'm gonna find the value of the C1 and C2. This two term doesn't have anything related to C1. And if I want to get the derivation respect to, for example, C1, here the result is C1 of phi is equal to integral of 0 C1 of phi is equal to 0 x y 1 theta h of phi x y dx dy over the area that I get do the summation for this value, which is h of phi xy dx dy. Here are the summation of the values, and here is the area that we do the summation, and in the same way the C2 of phi is equal to integral of u0 x y h 1 minus h y x y dx dy over the okay, and here this is the average of outside, and this is the average of inside, and I don't know. Okay, I think I have time. suggestion in this paper for the H. As I didn't talk about, the H was a function, something like this, and they suggest a function. I got H1 as epsilon, which is equal to 1, 0, and 1 over 2, 1 plus c over epsilon plus 1 y sine p c epsilon 1 when c is bigger than epsilon, then c is smaller minus epsilon, and epsilon. The shape of this one is some sinusoid, and for H2, by using this one in the result of the paper, they showed the this function that we change it here based on the H. This function, they use only the local information, and the curve that they find here is not necessary to be the global minimum of this function. But for the second one, 1 epsilon, which is equal to 1 over 2, 1 plus c over y of r times c over epsilon. This one is something like this, and if I wanna draw the here the delta function, this is the u and this is the delta 0. For here is, for the first one is and for the second one is something like this, but it's very narrow after. And by using this one, the result shows the initial curve cannot affect the result of the optimization, and the curve always will fit around the image. And that's point. I think I can go a little around to the detail of the how to implement it, but I found the code, and I don't know if you want, I can show the result in the beast on some sample images. If you have any question, I have two options. I can go through a little how to numerically calculate the value, or go through some, or if you have any question, I can.
How do you find the minimum exactly when this case here?
For the finding the minimum, they try to find the changing of the phi for each point ij n plus 1 minus the ijn over delta. Delta is the step of the changing, and this is the phi for the iteration, one iteration compared to the next one. And they use this delta t and the changing of the variable, and use the function here. They use the delta h. It's a little big term. I'm trying to fit it. It has two terms. If I want to say this is the f function, and the first term is as the first term is depend on the divergence of the gradient of phi over the delta phi, but they use the changing of the value function here by approximating the value of h of delta of h of phi ij and multiple to this value. In the original one, write it on the row fiber is equal to a 5 minus lambda 1 and 0 c square minus lambda 2. This is the ratio of changing, and when this ratio is equal to 0, it shows there on the boundary. And they assume this one is equal to 0. If you remember, in the previous cases, instead of these two terms, there was here, instead of this delta, it was some function of derivative of phi x, and here, instead of these two, they had only mu, or they had mu multiple g of the delta u0. This is the big change in here. In the introduction, I talked about these techniques. They are depend on this value. If this value is equals to 0 is stop the function. But here, the stopping condition is this similarity. And this U0, it's the intensity of each pixel, but they said it is not necessary to be the intensity. It can be, for example, the derivative instead of the, for example, U0, you can use the some gradient function inside the U0. For example, if you have an image that let me, and the rest is something like this. And this technique can, for example, start with some initial curve here, and after that push this one to this area. Instead of using the intensity of each pixel, they use the gradient in each point and use it here for the stopping condition. And based on these two functions here, they have some equation to how to use this h epsilon here, and there is a little changing here to, for example, finding the derivative of d over dh. There is a formula that, if you want, I can explain it fast.
You stop here. You do great material.